be discussing about the starting methods of the synchronous motors, because we know that the synchronous motors are not self-starting, so we have to start by certain means. So today we'll be discussing about the starting methods by either by having an auxiliary motor or by providing damper windings on the synchronous motors. Uh, then the working of the synchronous condensers, because mostly that is the application, and the hunting in the synchronous motors and its major applications in the practical world. So how do you start a motor? The first method is the by means of the auxiliary motor we will start the synchronous motor. That is, first the auxiliary motor is being run, and auxiliary motor, once it achieves the maximum speed, then you will uh, switch on the synchronous motor field supply and cut off the supply to the auxiliary motor, because if the auxiliary motor is still connected to the synchronous motor, the auxiliary motor will act as a load on the synchronous motor. Hence the auxiliary motor supply is being cut off and you have got the synchronous motor supply. So the synchronous motor DC switch, when it is closed, the rotor poles are pulled up into synchronism with the rotating field, and it continues to rotate until either you stop it or the load increases the pull-out torque. The second method of starting the synchronous motor is that we first start the induction motor. We first run the synchronous motor as an induction motor, and then we shift over to the synchronous motor. So to run the synchronous motor as an induction motor, we provide the windings on the pole shoe, and this pole shoe will provide the windings on the pole shoe is known as the damper windings. They are short circuited. So you know that the induction motor rotor conductors are short circuited. So this will run first as an induction motor, and once the no load speed is achieved, the supply is being given to the field, and once the supply is given to the field, the rotor picks up the speed to the synchronous speed, and therefore the damper windings will be now disconnected, and there will be no current in the damper windings under the synchronous speed condition, because you know that at synchronous speed the relative speed is 0 between the rotor field and the stator field. Hence there will be no induced current EMF and no current in the damper windings. So damper windings is basically just to provide the starting methodology for the synchronous motors. So once the 65% of the synchronous speed is achieved, the rotor winding will be connected to the mains and the machine will be running as a synchronous motor, because there will be magnetic locking between the rotor field and the stator field. Now this is the major part or the major application of the synchronous motors, that is run as a synchronous condenser. This is basically meant that where there is low power factor, there we use the synchronous motors for the improvement of the power factor, because for the industrial applications, if you use the power at a very low power factor, you may have to pay the penalty to the utility who is providing you the electrical power. So to maintain the power factor near to the unity part, you have to have some methodology for the improvement of the power factor, because most of the industrial loads are inductive in nature. So you will have the lagging power factor only. To improve the power factor of the utility, you have to have an overexcited synchronous motor which will work as the capacitor, and hence the name has been given as a synchronous condenser, and so that the motor, it doesn't drive the load, it is just used for the power factor improvement. So now over here you can see the circuit diagram. This synchronous motor is working as a there is no load on it, but it is connected to the power line, and you have got the initial power as the lagging power, and when you connect this synchronous condenser, then your power factor has been improved, and you get the new power factor as cos phi 2. So you get a better power factor when you connect this synchronous motor, because this is the power input for the synchronous motor. This gives you a leading power factor, and so the total power factor is improved. So from cos phi 1 you have improved to cos phi 2. So this was initially being used in most of the industries, but at the present day you don't have much application because we have got good supercapacitors, good capacitors which can be having a automatic control by measuring the power factor, or you can have the power electronic based power factor improvement system. So present day not much use of synchronous condensers in the field, because this will be costlier as compared to the other options available. Now there is one specific phenomena which occurs in the synchronous motors, that is when there is sudden change in the load or excitation, either removal of the load or addition of the load, the power angle changes. So when there is sudden change in the power angle, the rotor lags behind, it doesn't change instantaneously. So that change in the power angle oscillates for some time, and then it settles down to the new load position. So that oscillations is known as the hunting of the given motor. So this hunting happens in the alternator as well as the synchronous motors, and it can be prevented by providing the damper windings to the given motor. So basically what are the causes? The causes are the sudden change in the load, sudden change in the field current, that is excitation system, cyclic variation of the load torque, sometimes the load torque itself varies, and maybe some fault has occurred in the system that produces hunting in the synchronous machines. So what will be the effect of hunting? The effect of hunting can be that the machine can go out of synchronism, its a motor will stop running, or if it is generator, it will be out of step operation. Large mechanical stress may develop in the rotor shaft, and the shaft may be distorted, and you may have to take a breakdown to maintain the rotor shaft. Second is, there may be resonance condition appearing in the machine, and it happens when the frequency of the torque component becomes equal to the transient oscillations of the machine. So this hunting also increases the machine losses and overheats the machine, and it may cause the variations in the supply voltage when you are using as a generator, and you may have the flickering of the lamps which is connected to that supply system of the generator. Now what are the applications of the synchronous motor? The synchronous motors are being used mainly for the improvement of the power factor in the large industries. Many substations were also using synchronous motors as condensers so that the power factor can be improved. They are used to control the voltage end at the transmission lines, again with the varying variation of the excitation, so that you can maintain the power factor of the given transmission line. Some industries where you need a constant speed only, that is your textile mill, cement factories, mining industries, rubber mills, they all need a specific speed application. There the synchronous motors are used. So these motors can be used where the constant speed operation is required. It can be used for centrifugal pumps, fans, air compressors, motor generator sets, etc. But because these motors are costly, plus you need the double excitation for the operation of the synchronous motors, so most operations are being replaced by the induction motors or the single phase induction motors if it is a small application, or three-phase induction motors for the larger applications. So today we have studied about the starting methods of synchronous motors, then the working of the synchronous motor as synchronous condenser and its applications. Thank you.